Welcome to everybody. Thank you for being here today for this last talk of the fourth edition of this webinar series. It is my pleasure to first give you a couple of insights of where we are at this point. We've had with this fourth edition 27 talks, 12 lectures. We've had a lot of visitors on our website. You have a map here showing that we've been visited from pretty much all over the place. And then we have 200, and this is up to today, 216 YouTube subscribers with more than 800 hours of watch time. Now, this says that we are definitely not influencers yet, but I honestly take those numbers as a great success because I couldn't imagine more than 800 hours of watching people talk about rheology. And that's great. And last news from the week, we've made it on the bulletin of the British Society of Rheology. That's very nice, and we thank both the Society of Rheology, the British Society of Rheology, and Chris Ness for highlighting our initiative. And without further ado, it is really my pleasure to welcome Gareth McKinley. I think that everybody here knows Gareth, professor at MIT, and he's giving today a talk, a class about, well, the title is really spooky, even though we are in Christmas uh, time. The future of rheology is looking fractional. And so, Gareth, thank you so much for being here with us today and for accepting to dedicate your time to this project. And the floor is yours, people. As always, this is a class, and let's make it interactive. And just raise your hand. I'm sure Gareth is going to be very happy to be interrupted and answer any of your questions.
Absolutely, absolutely. I'm going to stop your screen sharing if that's okay. Um, and hopefully, let's see. Do you see my screen?
Perfectly.
Yeah.
Yes, yep. Um, okay. All right. So this is indeed meant to be a class format. So I'm happy to answer questions. The tendency with academics is always to go very fast, and I'm English, so I tend to speak fast. So if you got any questions, please do interrupt me or let me know. This picture below, it was taken this morning on my way to work. So this is what it's like here today. This is the River Charles. You're looking from the Cambridge side over to the Boston side, and the river's just about frozen now. So it's been cold. So this the river does freeze in the winter, and so we're just about there. So when I got to the campus, well, and actually, and before I start, just the names listed on here are just some of the people who have contributed to some of the work that I'm going to tell you about. So thanks to everyone that's listed here for discussions. But when I got to work this morning, this is what the campus looked like. The snow's just about all gone here at the moment, but you may have seen this image before. I think some of you may have seen this before, but since this is a Hitchhiker's Guide lecture, back in 2000, when Douglas Adams passed away, the Dome had this very nice tribute to him on a very large towel put across it, which it said, "So long and thanks for all of the wit." And I really do think that actually, as a kid, I grew up as a really big fan of the Hitchhiker's Guide to the Galaxy, listening to the radio shows as a 14-year-old. And I think actually in this device that we all hold in our hand, we pretty much have a hitchhiker's guide these days. Between this and ChatGPT, which doesn't quite have the attitude yet that the hitchhiker's guide has, but give it time, and I think someone's going to have a version of ChatGPT that has the same kind of snarky attitude. So anyway, I hope that I'll do Douglas Adams some justice on this. So. So first of all, since we're on a journey, I hope everybody knows where their towel is. ChatGPT made me one this morning, so we're going to talk about the fractional Maxwell model or fractional derivatives, and this will be hopefully helpful to you as a guide. And remember the immortal words of the Hitchhiker's Guide: "Don't panic." So, if you'd like a copy of the notes, the easy way of distributing them, I'll leave this on the screen for a minute here. You can download a PDF of these slides. So, if anybody would like to get a copy of this so that you can write on them, please do go ahead. I just ask you not to distribute them. And I've tried to point you to references on the literature on some of the slides as well. Okay, so what I want to try and cover in this class is, first of all, a kind of a motivation for why I think these ideas are good. And this really leads in the physics community to the ideas of fractional diffusion. And then I'll give you some ideas of the background for what fractional differentiation is. And then the kind of canonical model, the simplest model, often is called the spring pot. It's a combination of a spring and a dash pot. The name probably to give to it is an English rheologist called Scott Blair. And so many people will call this the Scott Blair element. Once you've learned how to use that, you can build your own models using these ideas, including things like the fractional Maxwell and the fractional generalization of the Kelvin-Vogt model. And then I'm going to show you some applications of how to do it. I don't think I'll have time to get to kind of current interests, which include data-driven ideas and using things like Bayesian criteria to help with model selection. I did include those in the PDF of the notes, so you may have some extra time to look at those. And I'll say that I didn't always believe in the ideas of fractional calculus. In fact, many times when I looked at papers in the literature, I thought, well, really, these are ideas for mathematicians who just don't have access to a good computer and can't do simulations. But Don Plazek had similar ideas about some things that he was interested in, and he made this wonderful quote, quoted this poet from Germany, Novalis, that says, to become properly acquainted with the truth, you've got to first have disbelieved it and maybe even fought against it. And I certainly never used to believe in the ideas of fractional calculus. However, now I'm an acolyte or someone who's a believer. And so I hope to convince you after this lecture to believe in these ideas as well. But if you're doubtful or skeptical, then that's absolutely understandable. But so the motivation, why might you be interested? Many of us are interested in things beyond polymers these days or beyond simple materials. In particular, might be interested in building materials that are held together by, for example, fillers or hydrogen bond interactions or hydrophobic groups or things that generally lead to things that are bigger than a single molecule and that you might call a supramolecular material. Um, and so just illustrate the kind of thing that can happen. This is a nice plot of G primed and G double primed that we're all familiar with for a polymer melt. In this case, a polybutadiene. And then they're going to just simply modify the molecular weight, which is pretty small here. And they're going to do that by adding side groups that allow you to form interactions from hydrogen bonds. These are called urazole groups. And essentially just going to modify these molecules by about 2%. So just about a 2% modification. If you now measure G primed and G double primed from a material like this, you get a curve that looks like this. And so the classic regimes that we learn to look for, like terminal regimes where the slope of G primed is 1 and the slope of G double primed is 2, completely disappear. And get replaced by things that look much more like power laws. And so you can see that I have a power law regime that transfers to another power law regime. And if you want to think about modification or bang for your buck, if you like, I put in 2% of this modifier, but if I pick a value, let's say like a frequency of 10 to the minus 2, and I look at the viscosity, it went up when I added 2% of this polymer, the viscosity went up about 3 orders of magnitude, so about 1,000-fold. And that's from physical interactions between the chains. And so this is a very good way of modifying a material. But clearly, the kind of models that we might think about, like a Maxwell model or something, or a reptation model, are not going to be very good for describing these kinds of materials. So we might like something else. I took this example from a great book chapter, which is where I first really learned about some of these things from a group of German rheologists, particularly Christian Friedrich and collaborators. And so if you want a really good introduction to this book chapter from 25 years ago is an excellent book chapter for getting a first feeling for these kinds of ideas. So that's our motivation is can we describe this kind of curve or these kinds of curves that we see here? Underneath it, at the background of it in the physics community, really what people have become interested in is what's called fractional diffusion. And that essentially will allow us to understand where these kind of power laws come from. And the idea really is to generalize what we all learn about when we learn about physics in terms of a random walk, to think about a more general form of a random walk that's sometimes called a continuous time random walk. So when we all learn about molecules bumping into each other, we talk about the molecule colliding and then bouncing off and going in a different direction. But what about when they collide, if they're sticky? If these hydrogen bonds lead to a weak interaction for some time, then maybe I stay stuck together for a time before I move away. And so I have to understand a more general process. And what that leads to is a kind of relationship that looks like this, where the mean squared displacement no longer grows linearly in time, but grows subdiffusively with an exponent that's between 0 and 1. And this is often called anomalous subdiffusion in the physics literature. If you look at the distributions that are associated with that, I no longer have a Gaussian distribution of steps. I actually have, because I get stuck together, I have a much narrower distribution. And so I don't travel as far. I stay more time at a small displacement. And so I lead to this very non-Gaussian looking like distribution. But if I go through the process of developing a diffusion equation from this, what you end up getting is what's generally called a fractional diffusion equation. So it may look like the classic mean squared or the second order derivative of the probability distribution in X, but it's a non-integer derivative of the probability distribution in time. So this is the first indication that there's something that we'll call a fractional derivative. And if you've ever seen this before, you might wonder about how that's going to be connected to rheology. Now, the amazing thing with modern NMR techniques is you can actually look at diffusion of labeled particles. And so this is actually diffusion through cheese, through a block of cheese. And the brightness here is a measure of the velocity that's measured. And what indeed you'll find is that the Brownian motion is not a normal kind of Brownian motion, but in fact actually remains stuck or trapped for a while. And then there are regions where it moves fast, where it's brighter, and then regions where it slows down again. And so you can actually see this kind of non-classical diffusion in things like a block of cheese. And we'll come back and see that fractional calculus is a particularly good thing for many food materials. So this will lead, if I solve this fractional diffusion equation, it's going to give me this kind of idea of the mean square displacement. And with microrheology, you can actually see this. And if I use the generalized form of the Stokes-Einstein equation, that I can measure the mean square displacement, then I can go from the Laplace transform of this mean square displacement to calculate a modulus. And what you're going to find is that the connection is that when I put this back into the real-time domain, is that we'll find that the modulus does not relax like an exponential, but in fact, the modulus is going to relax like a power law. And this exponent is directly connected to this exponent of the fractional derivative. And underneath it, it's directly connected to this mean square displacement. So we have to keep track of exponents, but it'll show up either as a mean square displacement or as a relaxation in time. And so my first exposure to fractional calculus was when you start to measure things that look like power laws. You ask, well, it's not an exponential. What is the physical process that gives rise to this power law? And you can see this very nicely, for example, in something as simple as a gel. So this is a laponite gel. This is a material made of a synthetic clay. You mix it up, you put some particles in it. And if you put some particles in and you look at the mean square displacement, you'll get a random walk. And if you measure the mean square displacement in time, you get a nice slope of exactly 1. And that slope tells you that it's basically a Newtonian fluid. And from the value of this, I can calculate, if I know KT, I can calculate the viscosity. But if you wait 15 minutes and you come back and look, then your power law looks quite different. And the same material, it's got the same traces in, but now the diffusion is much slower, and the material is beginning to build itself up into a gel. And by the time you wait 30 minutes or so, then you'll find that the mean square displacement is still a power law in time, but with a slope that is much, much smaller. And so just as simple as something as mixing a clay up and putting it under a microscope, you see this transition quite naturally. And so something's going on the microscopic scale that's connected to this idea of a change in the diffusive properties. So that's what's going on underneath it on the smallest scale. If you're interested in theory, if you're a theoretician, you're interested in developments in this area, there's some nice papers in the literature looking at the microscopic roots of this. What it really comes down to often is the idea that the idea of a delta correlated process in the Langevin equation is no longer correct. So I don't just bang into things and then move away. I actually stick together for a while. And when I incorporate that, then I'll start to see that I don't get a classical kind of Langevin equation. I get a generalized form. And this gives rise to things like Rouse models, but with fractional exponents. And so that people are beginning to unwrap some of the theory at the root of this. So that hopefully will give you a kind of an understanding on the microscopic scale. If you're an experimentalist, a picture's worth 1,000 words. Here's some examples of systems where these kinds of ideas show up. This is actually a waterborne paint. If you've ever painted your wall with a waterborne paint, you really deliver a dispersion of polyurethane droplets. And as the water evaporates, they start to build structures that are interconnected. And if you measure G primed, you'll find that G primed increases in time, but also the slope of G prime changes. And as the paint dries, you get a more elastic material, but you can very clearly see that it looks like a power law. Here's another example of a material I'm very interested in at the moment, which is saliva, which is a mucin network. And a mucin network forms something that really doesn't look like the classical model of a single chain or a bead and spring network. You can see that it forms this very interconnected network held together by disulfide bonds and hydrophobic interactions, which are very, very sensitive to pH. And we'll come back to this later on in the talk. But if you take mucin at the pH in your mouth, it's about a pH of 6. It's a weakly viscoelastic liquid. By the time mucins get into your stomach, where the stomach is more like a pH of 2, then it'll naturally build itself into a gel that again looks like a power law. This is really important in coating your stomach with a small gel lining that helps you prevent from dissolving your own stomach, in fact. So the formation of a healthy mucin network is extremely important. And again, you can see that just changing the pH changes the rheology by factors of 10,000 or more. So there's many cases where you'll see these kinds of power law responses. Sounded like I heard some audio. Was there? I'm happy to pause for a question if anyone had a question. Nope. Okay. Okay, Michael Peter, I see your memories. You don't miss those winters, huh? Well, nice to see you online anyway. Um, all right, so I mentioned mucins, but we ourselves are a complete collection of power law materials. In fact, actually, so here's an example from the London Olympics of some synchronized swimmers in their bodysuits, and if we look at each of the individual components here, the liver and kidneys, if you measure G prime and G double prime, they often look very much like power laws. If you look at lung tissue, it's a fractal distribution of cells. And if you measure, for example, how the pressure relaxes with time after you've inhaled, what you'll find is that the pressure doesn't relax like an exponential. It is indeed more like a power law. And people will fit it with this idea of a spring pot. If you look at airways, your trachea, for example, then again, if you look at the elastic modulus of your trachea, it's kind of a power law. And the interesting thing is you can change the rheology, for example, by administering drugs. And so you can make the viscoelastic properties of tissue change quite a bit by changing, for example, the drug that's administered. And final, I see a question. Let me just finish the slide and then I'll come back to it. Here's a final example of the red blood cell membranes. This is something that Subra Suresh here at MIT measured a lot of properties of. And again, they turn out to have a very fractional-like response. Interestingly, for those of you who know about large amplitude oscillation, people have done large amplitude oscillation measurements on red blood cells. And I always rather like it because the shape of the Lissajous orbit actually looks remarkably like the original material, which I find rather nice. Was there a question? Michelle, you've raised your hand.
Yeah, there is a question from the chat, so I'm gonna just
Okay.
read it out. Mucin, and you compare it with polyurethane. Is this some connection?
Sunny, no, I'm just trying to make examples of the breadth of materials which show these kinds of responses. So I don't think there's any connection really, except for the idea that they're supramolecular. Polyurethanes are great examples of materials that have soft domains and hard domains. Hydrogen bonding interaction is important between them, and so it's not just a kind of a bead spring network, but it's a collection of multi-scale interactions. All right. But great. Thank you for the question. We'll move on. Um, so some of you may know this movie. It's a rather old movie now, but you might know this movie where Bruce Willis says, or Haley Joel Osment actually says, "I see dead people." The equivalent for me is that I see power laws. So everywhere I look, I see power laws. If we look at the Hitchhiker's Guide, however, Zaphod Beeblebrox might say, "I see opportunities." So there's a great opportunity here for modeling of these kinds of complicated kind of materials. So that's what we're going to try and think about. If you want to learn more, these are the three best books that I know on learning more about it. The one on the left has the benefit of being a paperback and in the Dover series, so it's only $10. The one on the right is much newer. My favorite book, however, is this one. If you really want to learn the mathematics of fractional differential equations, Igor Podlabny's book is a beautiful one. So maybe take a look for that in the library or buy a copy, but it's really nice. I'm going to just give you a one kind of page, very quick introduction to these ideas. The interesting thing is fractional calculus goes right back to the origins of calculus, goes right back to Leibniz, in fact, who wrote a letter that he sent to L'Hopital. And many of you probably remember L'Hopital from L'Hopital's rule. The interesting thing is there's no record of a response that L'Hopital ever wrote back because I don't think he had an answer. But Leibniz's question was basically, why are we only using integers when we learn about derivatives? What stops the integer from being an element of the real numbers? So we all learned when you learned about calculus, you learned how to take a first derivative. And then you learned that if you take a derivative of a derivative, we'd call it a second derivative and a third derivative and so on. Well, the same thing can be done and can be generalized quite nicely if I just make this exponent a real number. So for example, if I can define for you in a minute what a half derivative is, if I take another half derivative of a half derivative, I must get the first derivative. And so those kinds of ideas that we learned about when we first learned calculus can be generalized. Certainly when I was learning calculus, I was spending time trying to figure out what the hell was going on. I never thought, what about if it's a real number? But that's really what it comes down to. And since then, a wide number of mathematicians have used these ideas to solve a number of problems. Lots of them are in electrical engineering, lots in analytical electrochemistry, and growingly, I'd say, in viscoelasticity. So the first thing to note, for example, is after this generalization is that this operator that we're going to introduce is still a linear operator. So if I apply this operator to a combination of two functions, I'm still going to basically differentiate the individual functions. So this is going to be really connected to the ideas of linear viscoelasticity. So it is going to be a linear theory. But because it's a linear theory, we can use Laplace transforms and Fourier transforms still. And the formal definition that turns out to be useful, and I'm not going to have time to go into the derivation of this, is actually only something that was really settled in the 1960s. So even though this started in the 1600s, it was only about 300 years later that people really got to formalize. The proper way to define this was figured out by an Italian called Caputo. And this is the definition that we'll use for the derivative. So notice it's a fractional derivative, but it's actually written in terms of an integral operation. And of course, when we learn calculus, we learn that the reverse of differentiation is just integration. So these two are connected to each other. And so I'll go a little bit more into the detail of this. But for example, if I just multiply this operator, if I just put a constant in front of it, then the equation on the right might be something that you might start to say, hey, that looks a little bit like what I learned about when I learned about the Boltzmann integral. So it looks remarkably like a Boltzmann integral. And the only thing that I need to get a stress is to put something in front of it that's going to have the right units to get a stress. And so this is already the simplest constitutive equation for a fractional material. And I'll explain that a little bit more on the next slide. But really, this is what comes down to the history of this. Okay, so as I've mentioned, Leibniz started this idea. It's now been formalized in terms of this idea of the Caputo derivative. And it's really by developing the idea of thinking about the idea that integrals and derivatives are just related to each other. And so one way of thinking about taking, if I asked you to take a 1/3 derivative, is to actually integrate by the 2/3 power and then take a first derivative, because we know that if you go up one order and down one order, I'll get back to where I am. So, for example, if you ever needed to calculate the third derivative, you could take the fourth derivative and then integrate once. So this is very nice because it means that I only have integer derivatives. And then I have fractional integrals. So again, as an example, if I asked you to take the 1/3 derivative, you would integrate by 2/3 of a power, which is this part here, and then you'd take one integer derivative. So m is an integer, and it's basically the smallest integer that's bigger than the fractional exponent. Why is this useful? I'm going to explain why that is in a minute, but it basically comes down to the idea that we all have a good physical understanding of strain and strain rate, and maybe the second derivative of strain rate, but we don't really have a good fractional idea of a fractional rate of change of strain. So this is a very handy mathematical way of doing this in terms of thinking about integrals and derivatives as being inversely connected. I mentioned that it's linear. I mentioned that we can do Laplace transforms. When you take a Laplace transform of this, we're going to get something that looks like it contains my transform exponent to some power. And then there's a bunch of additional terms that come from initial and final conditions. And again, the nice thing about using this Caputo derivative is that in rheology, often at time t equals 0, we might say the strain is 0, and the strain rate is 0, and the second derivative of the strain rate, and so on is 0. So many times these extra terms go away. And then the Laplace transform indeed just has this very nice simple form like this. And the Fourier transform is just a complex generalization of this, but it's immediately going to give rise to power laws, I omega to the alpha. And we know that we start to see omega to the alphas when we were looking at those G primed and G double primed measurements. So this is the linear part of the theory. This is the operator. I can only really give you a quick introduction to it, and I'd recommend these references for more details. And what we're going to do is we're going to incorporate this fractional derivative now, where alpha is between 0 and 1, to replace the things that we learn when we learnt about viscoelasticity and to replace springs and dashpots. If you'd like a physical interpretation of what's going on inside the material, this is challenging. The best description I found comes back to Igor Podlubny, whose book I recommended earlier on. And really what it comes down to is the idea that when we think about time in the lab environment as moving through like this lecture at every 1 second, 2 seconds, 3 seconds, 4 seconds. But you probably all are having your own experience of time, and maybe time is going really slowly for you right now, if you're finding it really boring. Or maybe it's speeding up if you're beginning to be really excited about it. So the idea is that inside a material, the rheological timescale may evolve in a different way. And a good example or a good analogy of that is if you think about the sun moving past a fence, the sun moves at a certain speed, but the shadows may actually move at a different speed than that. And so really the idea is that laboratory time and rheological time are evolving at different rates. That's the kind of physical idea. So if I have sticky diffusion, if my mucin network is held together, then even though the clock is moving at a regular Newtonian kind of timescale, the material itself may be relaxing on a very different timescale. So I find it a useful physical picture to think about this. And the person who really first thought about this in rheology was a British rheologist called George William Scott Blair, a good English name. Here's a picture of him at the end of his life wearing a medal. It's actually not the Bingham Medal. If you look, it's actually what was called the Poissy Medal. It's actually the rheology, the Biorheology Society used to award a medal. And he really thought a lot about these ideas. The best description in his biography from Howard Barnes was that he was described as the quintessential eccentric Englishman. And you may be thinking that I'm the same kind of thing right now, talking about fractional calculus. But these ideas of fractional differentiation were indeed his attempts to try and understand real materials in real situations. And many of you listening probably are dealing with those kinds of things still, right? About trying to understand really complicated materials, far more complicated than the simple ideal things that we see in a textbook. So I think fractional calculus is particularly useful for understanding those kinds of things. Here's an example. Here's a real world material. This is a low density polyethylene from BASF. It was a benchmark material 50 years ago. And people would measure G as a function of T and try and describe the rheology. And what they'd find is that to quantitatively describe the rheology, you might need multiple relaxation modes, and you might need time constants that span 7 orders of magnitude, right? And that corresponds from the shortest part of the polyethylene segment all the way up to the longest branches. And of course, what we learn is the idea that what you're really doing is you're adding inside the material multiple springs and dashpots. And every mode describes a little bit more of the material. But to really get a quantitative description, you need at least 8 modes. And even with 8 modes, you can probably see that this curve doesn't look perfectly smooth. It looks like it's bumpy. And I certainly don't see the bumps in the real data, only in the fit. So something's not ideal here. And Churgill had a nice quote about this, that at some point, the minute you start adding this many parameters together, all of the physical simplicity that we learn about when we learn about a spring and a dashpot kind of go away. And you start making arbitrary decisions. So for example, who decided that these time constants should be exactly 10 to the 3, 10 to the 2, 10 to the 1? That was a completely arbitrary decision. Maybe there's a better way. Maybe there's a better way of describing this kind of data than just adding 8 springs and dashpots together. And that's where I think fractional calculus really plays a role. That was in a polymer melt, but here's a colloidal gel. Again, you see a nice smooth relaxation. I don't see anything that looks like a single exponential. This is a log-log plot. I see a power law, and I see a power law over at least 2.5 or 3 decades. Here's a bread dough like material. And again, it looks like I see a power law now over at least 3 decades in rheology. So in many real materials, there's so many interactions going on that there's not really a nice simple inflection point or something we can detect. And you start to see power law spectra. And that's where fractional calculus is going to play a role. So in a 1 hour introductory lecture, I can't really tell you all of the different ways that you can get to power laws. But here's at least a survey of some of the things. If you're interested in polydispersed polymer melts, the minute you put a distribution in of a broad distribution of molecular weights, you're going to get a power law-like description. If you're interested in colloids and what's called SGR or soft glassy rheology, the idea again is that I spend some time in an energy minimum. I might then jump out of it to a new minimum, but now I'm going to spend some more time in there. And so again, it's not a normal Brownian process. It's an aging process. This is going to lead to power laws. And if you're interested in partially cross-linked elastomers, where you have long dangling chains, they also will eventually lead to power laws because I've got a distribution of chains of different lengths and they relax at different rates. And so all of these can go into the mathematics that will lead to a description that's basically a fractional model. Michelle, yes.
Yeah, another question from the chat. Is this a good model for carbopole or in general EVP materials?
I'm not sure who asked that, but a material that's a class of materials I'm super interested in at the moment. We're part of the way towards a model for that. Everything I'm going to tell you about in the rest of today does not have a yield stress in it. So the disclaimer is I don't think at the moment there is a really good model that includes, for example, a yield stress. So this is very good for lots of different viscoelastic materials, but not so much for materials that have a yield stress. Stay tuned. I see it's Sharia. I would be very happy for other people to develop something that is consistent with that. Okay. So still to be done. I think the final piece of this that we need for the basic ideas is to recognize something about the properties that we're going to get out of these power laws. And Scott Blair described them as quasi-properties. So I'm going to use the same language. I'm going to call them quasi-properties. And interestingly, that even back then, so this was in the 1940s, he worked with another PhD who was actually a psychologist. So this is not a chemist or anything like that. This person was actually a psychologist, and they were very interested in this idea of perception of different properties. And at least in English, we often use terms like firmness or stickiness or stringiness. I'm sure there are equivalent terms in French. But I call them the language of nesses because they're all things that we kind of know what they mean, but we can't really define them very well. They're intermediate properties. They're not really true properties, and they're things which are much less clearly defined. And I'm going to now motivate a little bit about that. Finally, I'll actually note that he was actually doing this at research at a place that was interested in dairy products, and this really came about from thinking about cheeses and the kind of range of rheology that you get in milk products and cheese. So he introduces this idea that if we have an experimental curve, you can either fit a number of exponential terms, but maybe that's becoming rather arbitrary, and maybe there's a bit of more of a generalization. And so the term that we're going to use is going to be a quasi-property. And I've already introduced the motivation when we introduced this idea of this fractional derivative. To get it to have units of stress, I needed to put something with a symbol that I've called G. G is something that's going to have units, and it's going to have units that has units of pascals, but it also has units of seconds to some arbitrary power alpha, because this has units of time to the power alpha or to the minus alpha. So I introduced this notation a number of years ago. Other people, Alessandra Bonfanti in particular, who's written some very nice work, uses a different notation, uses a constant C. And unfortunately, I'd say that we're still not at a very general set of notation here. So anytime you pick up a new paper, you're going to have to figure out what the notation is that someone's used. But in modern data-driven rheology, this comes down to the idea of the principle of parsimonious descriptions, or Occam's razor, which is the idea that the simplest expression is usually right. And it's much simpler to do this than it is to add an arbitrary number of exponentials. So from a data-driven point of view, these kinds of ideas of quasi-properties embody a lot of modern interest in data-driven rheology. Let's take a quick example. Here's an example of a g of t relaxing as a function of time. This is synthetic data, but the same idea is going to show up in real data. And so we see a power law. We can immediately recognize that the slope, we might say it goes like t to some power. But to get it to have units of a modulus, I'm going to need to have something in front of it. And this is going to be this italic v that I've written it here. And it's going to have units of Pascal seconds to the alpha. In industry, many times people aren't familiar with this, but if you've ever fitted a power law data to steady shear data, you're familiar with this. We often call the power law consistency K when you first learn a power law model. And we write it often as Pascal seconds to the n. That's a terrible choice, actually, really, because n is usually used by mathematicians for an integer, and n is not an integer at all. So I would say that we shouldn't really use n when we think about the power law model. We should use some other variable. But you've all seen the idea of something that has non-integer units before. And you might also have done this by, say, for example, if I compare, let's say, the properties of these three different materials, I might do it by reading off the value at a particular value of the shear rate or at a particular value of the time. And essentially what you're doing when you do that is you're saying, I don't really understand what's going on here. So let me pick out or pull out a reference time. Then I can write this time in the units of my reference time. This is now dimensionless. And then this thing up front now is going to have units that is going to have a real value, and it is going to have the units of a modulus. So we can compare these three curves, let's say all at a common reference time. Certainly when I go to industry, I find people use this kind of idea a lot. They're always going to say, it's a complicated thing. Let's just look at what happens at a given frequency. If you've ever done DMA, you often do this, dynamic mechanical analysis. You often just do one frequency and vary the temperature. So really what you're trying to do is understand the idea that it's a complicated property. It's got non-integer units, and that's what we're trying to get a handle on here. All right. Okay. So with all of that background and motivation, we can now look at some real data, I think. So hopefully what I've introduced to you is this idea of a fractional derivative. To get the units right, we have to put a quasi-property, which has got non-integer units in front of it. And then that will give me a stress. And really, the first person who did it in this form and did it in a way that's kind of recognizable to modern rheology was Köhler, about 40 some years ago now. But once you have this representation, you can see that it's very easy to specialize it. If I put alpha to be 0, the 0th derivative of strain is just the strain. So then I'm going to get a spring. If I put alpha to 1, then I get the first derivative of strain. That would be the strain rate. And then I'm going to get a dashpot or a viscous material response. So in general, we have good limiting values, and we can do everything in between here. And in rheology, we often like to introduce the idea of a complex variable or complex modulus. And so this is very useful as well. If we think about the elastic modulus as being the real property and the viscous modulus as being on the orthogonal axis, you can think about the Fourier transform of this as giving the magnitude of this, giving you the length of this arrow. And then the angle of this vector is given in terms of this exponent, pi alpha over 2. So for example, if alpha is 0, I'm going to get an elastic material. If alpha is 1, I'm going to get a viscous material. So we can span all of the limits by thinking about this property. Mathematically, you can show that this is exactly equivalent to a very special spring and dashpot network that's often called a hierarchical ladder model. So if I put springs and dashpots together in this particular order, the mathematical limit, when you take n going to infinity, gives you exactly this. And if you take the Fourier transform of this, I get a power law. If I look at the relaxation of this, we're going to get a power law in time as well. If you take the simplest description of the SGR model, if you say that there's an exponential distribution of energy states, then Adi Jaishankar and I were able to show that indeed the SGR model will give you exactly a power law. The front factor comes out to be set in terms of a number of things called gamma functions and these exponents. So if you take the SGR model, if you like this, you put in an exponential distribution of states, you will get a power law out of this as well. So that's a kind of mathematical representation of it. And I will call this the Scott-Blair element. And it's often represented in a couple of different ways, but often in terms of a triangle that can go to a dashpot or to a spring. All right, we're going to look at some data examples next. So let me pause right there and see if there are any questions. Any questions in the chat? I don't see anything on my side. Michelle, anything?
Nothing on my side either.
Nope. Okay. All right, let's continue on.
I'm still
Oh,
digesting this
oh, I
idea
see.
into.
Oh, okay. Yes,
So,
I realize it's a lot of digestion. The material is available, and I'm happy to answer some more questions at the end, but maybe it will help to look at some examples.
right.
So
Oh,
so
we do we
here's
do we do have a
oh,
question. Sorry,
okay. What is
from
the
the chat.
relationship? Oh, okay. I'm not sure. Is it Jose or Jose? What is the relationship? There is a power law relationship between them. I haven't given you that. It's given in here in this paper, and we'll actually come back to that in a minute. But there's a power law. There's a recursive relationship between these, and if you change that recursive relationship, you change this exponent alpha. So it's a great question. If any of you are electrical engineers or know friends who are electrical engineers, you might recognize that every time we show a spring is something that stores energy. To an electrical engineer, that's a capacitor. Um, to an electrical engineer, a viscosity that dissipates energy is a resistor. Um, this is a special thing that you can actually imagine making in silicon, and you can actually buy these chips that indeed have an arrangement of capacitors and resistors in exactly this way, so that if you put in a current, then you actually get the fractional derivative of that current out. And so you can actually buy chips that have this kind of relationship put together for springs and or for capacitors and resistors. And so it's called a spring pot to us. They will often call it a constant phase element in electrical engineering. All right, let's continue. All right, so here's an example, a very, very simple example, and I learned how to make these examples from Sebastian Manville and Thibaut Devou, and it's a simple milk protein gel that's cross-linked in a special way using a special enzyme. When you cross-link this material, you basically make a soft yogurt-like milk protein gel. If you measure the rheology of it over 4+ orders of magnitude here, it's almost a perfect example of a Scott-Blair material. And the slope of this, the exponent, depends, for example, on the concentration of the casein micelles that you start with. So you get almost a perfect power law. It's remarkably well described in terms of just two parameters, just our quasi property and our exponent. And so whether you believe the fractional ideas or not, I would defy anyone to find me a two-parameter model that can fit this much data that well. So in the principles of data-driven ideas of parsimonious descriptions, this is, I think, the simplest description you can get of these kinds of materials. But if it's a true constitutive model, we should be able to make predictions of other kinds of experiments. So for example, here's a creep experiment on the same material. Here's the strain as a function of time. You get these damped oscillations in a controlled stress rheometer. Many of you probably have seen this before because of the inertia of the fixture. The black line is the prediction of this with the mass of the fixture, and you get exactly the right damped oscillations. And at long times, you get the idea that d gamma by dt is not a constant. It's a power law that increases in time with exactly the same exponent of alpha of 0.15. Another simple experiment that you might do is a step strain experiment or a relaxation. Here's a step strain experiment on the same material. And again, you see G of T decreases like a power law. And again, you see an almost perfect power law over 4+ orders of magnitude. So this is about the most perfect kind of fractional Scott-Blair material that I know. If you were to look at the microstructure of it, you can again kind of maybe understand why. There's a nice, very broad distribution of structure inside here. It certainly doesn't look like a spring or a dumbbell or a chain or a monodispersed kind of reptation process. It's a very, very broad distribution of cell sizes and soft interconnecting material segments that give rise to this. All right, so that was the simplest model, but once you've understood that as a concept, all the things that you've learned how to do when you build constitutive models, you can do now. And a lot of this was done by Bagley in Journal of Rheology in two very, very influential papers. Last time I checked, this is the second most cited paper ever in the Journal of Rheology, and this is the fourth most cited paper in the Journal of Rheology. So these ideas have been around a lot. It's just I used to dispute against them and I didn't appreciate them, I think, but they really are the right way of describing complicated materials. So here, for example, is the fractional Maxwell model, which has got now two of these spring pot components. It turns out thermodynamically, to make everything consistent with thermodynamics, you need this exponent alpha to be between 0 and 1. And you need this exponent beta to also be between 0 and 1, and for them to be arranged in this order. If you do that, then these mechanical analogs turn out to be thermodynamically admissible. Similarly, I can put these two components together in parallel, and I can make what's called the fractional Kelvin-Vogt model. Again, I now have two elements added together linearly, and we will have the stress in this arm plus the stress in this arm. So that's really the kind of simplest kinds of realistic models that you can have. I'm going to skip the next slide in the interest of time and actually look at a comparison with some real data. So I'm going to take those ideas, which are, as I mentioned, are in the second and fourth most cited paper in the Journal of Rheology, and I'm going to compare it with data that's in the most cited paper in the Journal of Rheology, which is the paper by Henning Winter and Francois Chambon on indeed cross-linked polymer gels. And so here's their data from Journal of Rheology. And then here is a simple model. This isn't even a 4-parameter model. This is just a 3-parameter model. It's got one spring pot and one spring. And this spring is to represent the idea of the cross-linked network that is forming once I go through the gel point. And if I take that 3-parameter model, I can fit all of their data quantitatively, again, over now about 7 or 8 orders of magnitude in frequency, in terms of just 3 parameters. And so as the cross-linking process continues, the power law exponent decreases, the quasi-property increases, and the elastic modulus of this element increases as well. And so, again, I think that this is a very, very simple and very general description of a very complicated process. So it does quite well at describing these kinds of material properties. All right. So that's a very simple material. We'll move to a slightly more complicated material now. I've gone too far. Sorry. Let's go to this one. And what I'm going to show here is some materials now that are food-like materials. Foods are great examples of multi-scale materials. In fact, you may even notice it in the logo that food companies often use. They often recognize that their food is made up of materials that are very, very broad distribution of structures and have a very, very broad distribution of timescales associated with them. Here's an example coming back to what Scott Blair was interested in. This is cheese. And this was a visiting student from TU Eindhoven who came to me, who was very interested in cheese rheology. Cheese is a good description of a network that's got two networks. It's got a gel phase from protein and water, and then a dispersed filler phase that's fat, basically. That's what makes it taste so good. And so the compound material looks something like this, and these are confocal microscopy images. If you measure the modulus of materials, G of T is typically a power law. And if you take the fat out to try and make a low-fat cheese, you can put other things in to try and replace that texture. And maybe get something that looks like a power law, but often the rheology feels quite different and the mouth feel is quite different. And the way food people will characterize these things is often in terms of these kinds of ness, is like firmness or springiness or rubberiness of the cheese. This is often evaluated, for example, by touch or by sight. And these textural attributes are really connected with these Scott Blair ideas of fractional properties. And so it actually can be described by this Scott Blair model. And interestingly, the Scott Blair model actually indeed looks like the material that we're trying to describe here. This was done for a semi-soft cheese called Gouda or Gouda. And so I call this auto-rheomorphic. It's a material that actually looks like its constitutive model. And if I look at the relaxation here, we can also, for example, now predict things like the creep of cheese, the kind of thing that you see when cheese has been sitting on the shelf for a while. And so we can measure the creep compliance, and we can measure the recoil. And the recoil is connected to these kinds of ideas of things like rubberiness and springiness. And so these, I would say, the lines here, I should point out, are predictions, not just fits to data. They're predictions from this kind of measurement. I'm going to pause here. Michelle, I see you raised your hand, and Kalpit, I see a question. So can we use a fractional model with a simple spring or dash pot, referring to slide 27? Let's go back a little bit. Yes, we can. If I go back to this, we can take the limit of these going to 1 or 0. They're well-bounded limits, and we can get a whole range of different responses. So I skipped over this. If you're interested in playing with these things, if you go to Wolfram's Mathematica website, we uploaded a simple demo that would allow you to actually play with these things, and you can try these. And so these limits are all well posed, provided you keep beta and alpha within this range. Michelle, were there any other questions in the chat?
Nope, I was just pointing to that one.
Just the one. All right. Okay. So another great example, if you would like to ever make a fractional material, all you have to do is go to a pharmacist's or a chemist's shop and buy this material from Nestle. It comes as a dry powder. It's called Thicken Up Clear. It's made to help people who have trouble with swallowing or oral dysphagia. This is an X-ray fluoroscopy video of someone swallowing. And many people, as you get older, have trouble swallowing, and water will go down the wrong pipe. So one of the ways of controlling that is to thicken up the material. It's a mixture of starch and xanthan gum powder. But if you put in different amounts of this material into water, then you can get materials that have rheology that looks like this. And so you can span 6 to 7 orders of magnitude in elastic modulus and viscous modulus just by changing the amount of material you put in here. Um, and the lines here, the predictions, are nothing but a fractional Maxwell model with one additional thing, which is something that has the viscosity of water that goes into here as well. So this is often called the fractional Jeffreys model. And you can see how well it does at describing data. So if you ever want to make up a fractional material, go down and buy this material, and you'll be able to make a material that has a very wide range of properties. And I'm going to maybe conclude this main part of the talk here by connecting to then a way of representing this that comes back to something that Scott Blair tried to do back in the 1940s. He was interested in real industrial materials. He was recognizing that power laws were important, and he was trying to think about how to interrelate stress, strain, and time. And in many ways, that's what we as rheologists still try and do today. He tried to do it in a three-dimensional cube. I don't think well in 3 dimensions, so I'm going to project this down into 2 dimensions, and so we'll call this a Scott-Blair square. And so the idea is if we have a spring pot and we have two parameters, I can represent them on two axes. So I have this quasi property, and then I have a fractional exponent. That's naturally something that you can plot in 2 dimensions. If beta is zero, the limit of zero, of truly zero, back to Kalpit's ideas, it's truly the limit of an elastic solid. So nothing ever relaxes. I just have elastic stresses. If I go to a beta of 1, I'm in the limit of Newtonian fluids, and everything relaxes and flows like a Newtonian fluid. If I ask how big is the quasi property, I'll plot that on the horizontal axis. And now I can say how big something is. So I can say, for example, if I'm dealing with a fluid, I can have very low viscosity liquids, or I can have very high viscosity liquids. If I'm dealing with a solid, I can have very, very soft gels, for example, like a hydrogel, or I can have very rubbery solids, like, say, a rubber ball or something like that. So you can think about these two parameters as something that tells you something about how big something is, so a measure of quantity. And the exponent tells you something about the relaxing properties or a measure of quality of the material. And so I can represent a wide range of materials on this idea of which I'll call a Scott-Blair element. So let's actually try and do that with some real materials. So here's a whole bunch of different liquid foods that we looked at. Here's okra, tara gum, guar gum, flaxseed. Many of these are different materials. Here's saliva plotted on this 2-parameter axis. And then here's the material that Nestle developed, this thicken up clear, and how it changes as you add more and more amount of material. And so you can see that we change both the viscosity, if you want to call it that, but we also change the exponent beta. So we can move through this 2-parameter phase space just by basically more spoonfuls of material. The lines on here are lines of constant shear thinning viscosity. And they're evaluated at something that's recommended for the mouth, which is 50 inverse seconds. And there is, in fact, a government panel called the National Dysphagia Task Force. And they recommend that in your mouth, the shear rate is typically about 50 inverse seconds. And so here's the viscosity of water. Here's what they call nectar-like. Here's what people will call honey-like materials. And here's what people call pudding-like materials. And so this is something that's very common to people who are interested in dysphagia. All of these curves can be collapsed onto a rheological master curve. Kalpit, I see another question there. How was okra measured? The okra we measured was measured by buying powdered okra. You can do this by, for example, cutting okra open, squeezing out the contents, and then drying it or flash freeze drying it. So you can buy freeze-dried okra powder and then reconstitute it. So, at about 0.1%, it's a fractional material with a fractional exponent that's somewhere around about 0.5. So I think when we deal with real complicated materials, this is a useful way of trying to reference what material or what different materials look like. If I can beg the indulgence of the organizers for about just a couple more minutes, I'm going to address another question that was asked in the chat, which was something about are these, how do I understand these properties, or are they purely empirical? And so together with Emanuela Delgado at Georgetown, we started to take some of these ideas and try and compare these ideas with her MD simulations of real colloidal gels. And so they do simulations with a very large number of particles, and they look at colloidal gels where they have both pairwise interactions and three-body interactions that build a gel that has some stiffness. And here are the particles that might go into a gel. And if instead I replace the particles by the strength of the interactions between the particles, then I can think about a particle network that looks like this. So you might now want to think about the connectivity of the particles, how strongly they're connected, how many they're connected to, whether they branch or whether they're connected to two particles or three particles. And you can measure the viscoelastic properties in a simulation or in an experiment very quickly using something else I've been interested in called chirps. And so many of you may have seen something about chirps. This is just a very quick way of ramping through a wide range of frequencies so that you can measure the rheology very quickly. And what you'll see is that in materials like this, you start to give rise to rheology that looks remarkably like the power law models that I've just shown you. And here, for example, is the distance between branch points, shown where the branch points are colored by different color, depending on whether I'm connected to 2 or 3 or 4 or more neighbors. And so there's a distribution of these branch points that turns out to be a fractal. It corresponds to a 3D percolation network. It's not a DLCA or an RLCA network. It's a random percolated network. But when you look at the rheology of these things, they start to look remarkably like fractional models. And in fact, we can build a fractional recursive model that looks just like the one that I mentioned earlier on. And we can connect it, for example, to models that people have used to think about colloidal gels, where you have to understand the distribution of stiffnesses of the elements that make up these components. And the stiffnesses, for example, depend on how many neighbors you're connected to. And so at the end of the day, there is a rheological master curve that you can build. And you can describe all of these MD simulations over a wide range of different quench rates and a wide range of different volume fractions in terms of just a 4-parameter model that corresponds to this fractional model. So I think there is a connection to microstructural detail that allows you to understand how the fractal nature of the material gives rise to a fractional distribution of timescales. With that, my hour is pretty much used up, and so I'd like to jump to the conclusion now. So I'm going to jump to the conclusion and wrap up by introducing what I call the Rosetta Stone of rheology. If any of you know the Rosetta Stone, it's the same information given in 3 different languages. So on one side is ancient Greek, very mathematical. This is the language of fractional calculus. I've introduced to you something called the Caputo derivative. There's another function I didn't have time to introduce called the Mittag-Leffler function that's important, but this is really the Greek side of things, which if you're more analytical, you may find yourself naturally drawn to. If you're more of an experimentalist or an industrial rheologist, you might use terms like this. All of these are the languages of Nesses. It's what Marcus Reiner in his book called technological properties. They're not real properties, but we kind of all know what we mean. If we say a material is slimy or chewy, we kind of know what it means. And in ancient Egyptian, this was more of a pictographic language or hieroglyphics. So how do you get between the language of Nesses and the mathematics? Well, I'd say that's where the middle language was important. And on the Rosetta Stone, the middle language was the common language that was used in ancient Egypt at the time, which was called Demotic. And it was something that could be understood by both people, common people, as well as the priests of mathematics. And I think that's what I kind of view fractional calculus as. It's a pathway to go between a very mathematical description and a very applied or physical description. And I've introduced this idea of a quasi-property, and I've introduced this idea of a relaxation exponent. If you can get those ideas across, then I think you've got a basic understanding of fractional calculus. So here's a summary of things I've talked about. I haven't had a chance to talk about nonlinear properties, and I haven't had a chance to talk about cellular properties, but there are additional slides, and I draw attention to this recent paper that just came out if you're interested in single cell rheology as well. And with that, I'll just give thanks to the people who did all the work. Adi Jaishankar, Bhavan Keshavaz, Joshua Rathinaraj, Mohua Das, and Jano Vertulus are all people who I've been thinking about this with recently. And the companies who have supported this work are all companies who are interested in things that are complex, real-world kind of materials. If I've made you interested in this, I'd say if you want to learn more, together with Emanuela and Thibaut and Lawrence Ramos, we're organizing a summer school this summer in Cargés. Registration is now open. There's only a few spots left, so if you're interested, encourage you to register soon. And I would say, come on in. The water is lovely here, but make sure you bring your towel. And with that, I'm going to stop and happy to answer any residual questions. Thank you.
Thank you so much.
Thank you very much.
We do have a couple of questions and a raised
Yeah.
hand. I'd go, even though it was the last, I mean, I don't know actually the order, but let's start with the raised hand, Emilia, please.
All right, I'm trying to find my video panel so I can see people. Okay,
Thank
all
you.
right.
Thank you so much for the talk. It's been super, super full of information, but we have the support, so thank you. We'll go
Yeah,
through that. Actually, I had a question I'd like to link with the beginning. So when you talked about sticky dynamics at the very beginning, so
yes,
now I understand that this exponent between 0 and 1 would be now a fractional
yes.
process. Nevertheless, I want to understand how we can decouple two things that I imagine when I see this sticky behavior, sticky dynamics. So there's the polydispersity or the multi-scale dimension, and then there's also the interaction dimension, meaning that in your fractional model, there should be these two things that are described, right?
That's a great question. That's very perceptive. And yes, when physicists often think about fractional diffusion, they think about simple molecules or simple colloidal kind of systems, or maybe something that doesn't have its own length scale. So if you want to start introducing the idea that I have a distribution of length scales, then we know that the Rouse model is one way of thinking about that. And what you end up getting is indeed something that looks like a fractional Rouse model. In other words, there are still multiple relaxation modes, but the time derivative associated with each one of them may be a fractional exponent. So yes, there's a lot more complexity. In the language of physics, I would say it's projected down into a lower dimensionality, and that lower dimensionality is this single fractional exponent. But for example, in the fractional Maxwell model, which has two of these, an alpha and a beta, you might imagine that that's beginning to get at your concern, that there's more than one distribution of processes. So I'd say that's where that information goes. Which one you see probably depends a little bit on what frequency or what length scale you look at. And we kind of know that even from a real Rouse model. If I drive it at a high enough frequency, I see the rubbery network. I would say that corresponds to the high frequency exponent, which in the language and the slides I've used is beta. If you drive the system at much lower frequencies, then you will see things happening at longer time scales, and that might be the other exponent, which we call alpha.
Thank you. Thank you so much. I'll look into those two already and see if I can think of another one.
Yeah.
Yeah.
Okay, great. Thank you for the question.
We do have some questions in the chat. I'm just going to read them out for the YouTube people.
Yeah.
Okay, that's been answered. Humans often apply deformations to materials which are large enough in amplitude to elicit a nonlinear material response, but currently the quasi-static properties and uh, are only valid for linear deformations, correct? How can we make predictions of Ness properties from quasi-properties in this case?
Yeah, that's a wonderful question that I'm super interested in at the moment. I've jumped to a slide just so that we have something to look at while we're doing it. That's a much higher dimensional space. In the food world and in the consumer product world, this is where people start to go to what is often called PCA, or principal component analysis. And they'll start making diagrams that they often call spider diagrams, or they start looking at the different principal components that they can measure. And I would say that linear viscoelasticity provides the ground truth, or the two most dominant principal components. But for example, sliminess and stickiness and material properties like that are very much non-linear properties. They involve different kind of kinematics. Like stickiness is really a stretching flow or an extensional property. Sliminess is a strongly shear thinning property or a strongly non-linear property. I'd say the field is still wide open to try and really understand those. We've made some progress towards some of that, and I'm showing a paper here by Adi Jaishankar that tried to understand this for materials like xanthan gum, which is very much a canonical food additive that's used a lot. And we can understand the shear nonlinearity quite well now. So the slipperiness or the sliminess of it, using a fractional generalization of what's called the KBKZ framework, or the fractional KBKZ model. Do we have a good description of non-linear extensional properties like stickiness? I would say no. I think that's still wide open. How can you connect those principal component analyses that people do in the food world, or what some people call textural attributes, with the fractional calculus? Still to be done. And I hope I'll inspire some people to try that.
Thank you so much for the detailed answer. Now, another question from Nadia Nikolova. Nice to see you online. What is the interpretation of the beta plateau towards the higher concentrations for the Nestlé thickener, slide 37? Can it be connected to one of the Ness quasi-properties?
Yes, that's a very good question as well. There's some wonderful questions, everybody, by the way. This is great. I wonder if I can get back to slide 37. Yeah, so this work I skipped over, but this has just been accepted yesterday, actually, in food hydrocolloids. And this is joint work with Leonie van Taag's group in Melbourne, in the University of Monash. The lovely thing that was done here by Parisa Eslami was to connect measurements of the rheology with some exquisite cryo-SEM measurements of the structure. And this is in pea protein gels. And so the structure changes just by adjusting pH. And you can see that the rheology changes dramatically. On this scale, the rheology changes by about 3 orders of magnitude. This is simple enough that there's only a single exponent. So there's a direct connection between the exponent and the fractal dimension of the gel. Since I've got this slide open, I will say that another very useful thing in fractional calculus is something that people may know if you're a rheologist, called the Cole-Cole plot. If you're a control person, people often call it a Nyquist plot, but it's the same thing. But it's to cross-plot G primed and G double primed. In fractional calculus, this turns out to be just a constant. It's independent of frequency, at least for the critical gel. Yet everybody, when we teach a cold plot, we always say it shows a series of circles, of semicircles. That's only true because we think about exponentials, and we always think about exponentials. If you think about power laws, the cold representation is a straight line. And it turns out that in this case, all of the properties for all of these different gels lie on a single straight line that says that G double primed is a constant times G primed. And if I know that, then I can relate that directly to this fractional exponent. So the fractional exponent in time is encoding the fractal distribution of nature, and it's connected to the exponent that we typically see in frequency. So hopefully that is pointing in that way. This paper will appear early in the new year in Food Hydrocolloids.
Thank you. Another question in chat. Is there a review about the use of the fractional models on different classes of materials?
No, at least not that I'm aware of. The two best reviews of fractional calculus aren't really a survey of different materials, but they are great surveys of these models and how to apply them. They're both in soft matter. One is by Alessandra Bonfanti, and I think that's Soft Matter 2020. And then the other one is by Jake Song, who was a student of mine that's also in soft matter, SONG, and that's in 2023. So they don't so much cover different kinds of materials, though. They more cover different kinds of models. Subtle difference, but
Yes, nice. And finally, so they're just asking you to please show again the slide with the
I'm
QR
going
code.
to jump to that right
And
now.
and while you leave this on screen, I'm just gonna say that I knew almost, I mean, close to zero about fractional derivatives, and I mean, I knew about them. I didn't know anything about using them for constitutive models, and that definitely seems. I like this idea that these exponents do seem very closely related to things happening at the macroscopic level, and you showed that quite nicely here. So thank you so much. And I definitely need to well, don't panic here. I think it's really important for people to have and to remind. Um, but yeah, that definitely looks incredibly interesting, and I'm definitely looking forward to more of these results. And I really liked a lot these last slides you show about the work with the Manuela on gels and those kind of simulations, and how that really is connected to always this idea of neighbors and really how these interactions happen, how do they persist at some rates, correct me if I'm wrong. And it's really very mathematical, but also at the end very empirical. And
Yeah, it's good on the empirical side and on the mathematical side, and that's
yeah,
the my Rosetta Stone. But
exactly.
there is deep inside a gel, there is a fractal skeleton that you may not be able to see, but that fractal skeleton um, is projected in the real world by the body that we see of the gel, which is often a power law.
And how, like, if you had to describe what, like, at some point you show, I honestly don't remember the number of the slide. It was somewhere in the first part, I would say. It was an experimental picture. And there was this network of connections. And you said that not this one.
Okay, but
Very similar to the music networks, by the way. I don't remember the number. I'm
yeah.
sorry.
Maybe the cheese one,
I don't think it was the cheese, but
the
maybe
yogurt one.
Maybe the yogurt one. Yeah,
Yeah.
this one. Yes,
yeah,
yes.
yeah,
So how, if I really had to imagine to compare this to a dash pot, I mean, so sorry, to a spring
yeah.
pot, what's going on? Are these connections breaking when I increase the ampli deformation? And then, of course, they break in a very fractal way, and then when you decrease it again, they reform. And what's going on?
Yeah, yeah. So I think the better description, if I wanted to put something next to this, I would put next to it, not the single spring pot I had here, but really that representation internally, which is a series of springs and dash pots that are arranged. There is stress stored in each of these elastic fibrils, but you can see the diameter of the fibrils is very different, right? There's also relaxation associated with this. This is not a perfect elastic material. These connection points can actually move. They can actually break, form, they can slide along here. And so, and that all of those processes are happening. And you might look at this and say, there is no way I can ever describe that fractal distribution of things in a simple way. But the amazing thing is, when you take all of those processes together, you add enough of these processes together, you converge to something that often, I won't say always, but often is represented in terms of something incredibly simple, which is just two components. In many ways, Degen's contribution, the ability to see through an entangled polymer melt and recognize that what I really need to do is focus on a single chain and think of a tube and come up with an idea of an entanglement, was distilling an incredibly dynamic thing into a simple model. I'd say that this is the same idea for something that looks more like a gel, right? It looks
Yeah.
much more like that. And maybe the people who've thought about that are people far smarter than me, but people who have thought about SGR or thought about um, uh, partially cross-linked elastomers with lots of dangling ends. And when you put all of those processes together and you add enough of these processes together, each process itself may be an exponential, but you have a sum of all these exponentials that's summed in such a way that what comes out is a very, very broad of sum of exponentials that's nothing but a power law.
That's really beautiful. It's really nice.
I do have one question because I was wondering if you could do the same thing with like evolving entire materials, like maybe curing gels and stuff like that.
Oh, this is a wonderful question. And I had to skip over this slide. It is in the slides because I'd like to give some credit to a
Yeah.
beautiful piece of work by, again, Lise, who I met a number of times,
Alice.
who you may
Yes.
know. I think she graduated last year. I don't remember,
Yeah.
maybe
Yes.
within the last year. And I know that her thesis is a beautiful piece of work. But this is a great example of something that both Thibaut and I are very interested in at the moment. And provided you have a good separation of scales, so that the material is evolving slowly compared to the speed that you can measure it, then indeed you're beginning to see that, in fact, actually the process of gelation can be described in terms of a fractional
Yeah.
model. She uses chirps just like us. You look at tan delta and how it evolves in time, and you can build up these remarkably beautiful master curves that span 8 or 9 orders of magnitude in rheology. Her model that she needed to describe the data
Yeah.
quantitatively is more complicated. But for those of you listening, you now know all these components, and you
Mm.
know that they're linear, and you know how you can add them. I can add one component and another component and a viscosity. I can add a spring and this. So this looks like a
Yeah.
Kelvin Voigt-like material. This looks like a Maxwell-like material. So it's Maxwell in the sol state. I
Mhm.
go to a critical gel, and then I come out of the critical gel as a weakly cross-linked gel.
Yeah.
We've
Okay.
done this for laponite. Lise and Thibaut were interested in it for cellulose, but there's a whole bunch of questions I don't know the answer to, and I'd like to maybe end this recording and everything with this right here. Here are some questions that I don't know the answer to, but I'm super interested in. What sets those timescales? How do I
Yeah.
control the shift factors? The shift
Mm.
factors turn out to be horizontal and vertical.
Okay.
And there are some very interesting hyperscaling relations on either side of the gel point as I go into the gel and come out of the gel.
Mm.
And it doesn't feel right to me to have to switch models Nature doesn't know that it has to switch models at some point. I go to the gel, and then I come out at the other side with a different model. What I want is a single model that will take me right through the singularity. Those are the kind of things I'm interested in at the moment, and I hope maybe I've got some other people interested in them as well.
Yeah, that looks interesting. Thank you.
Yeah. Yeah. And I think you have. Okay. Um, Great. With that, I'm also gonna say just that I'm happy that I've quite often found myself lately. I've worked on chocolate, and very often I found myself using the language of Nesses, as you said, and I'm now happy that I can actually give it instead of Nesses using the other part of the Rosetta Stone that you
So
provided. Nice.
wonderful.
Okay. With that being said, thank you so much, Gareth, for this wonderful class. I think it's really a nice ending of this edition. And thank you all for being here. We'll definitely let you know what's going to happen next.
Thank you
And
all.
thank you again. I'm going to stop the recording here for the YouTube people. And